Okay, now straight to my class on inorganic chemistry. I'll be sending the material to you, but I also want you to listen to the video, watch the video, and then get acquainted with the concepts. Now, first row, transition elements and their characteristics. Okay, so the first row, transition elements are elements from scandium to zinc in period 4 of the periodic table. And then when we look at that, remember we have the first 20 elements. So these ones are coming just after the first 20 elements. So you have 21, 22 to 30, okay? And there you have it. So you have scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. Now to the characteristics. You need to know all of this. So what are the general characteristics? 1. Partially filled d orbitals. 2. Variable oxidation states. 3. Formation of colored compounds. 4. Complex formation. 5. Catalytic properties. 6. Magnetic properties. 7. Alloy formation. And that is it for the characteristics of transition elements. Now to crystal field theory. Crystal field theory explains bonding in coordination compounds based on electrostatic interactions between metal ions and ligands. So what are the basic assumptions? So their ligands are treated as point charges or dipoles. Interactions between ligands and metal ion causes splitting of d orbitals. Splitting affects color, magnetism, and stability. Now, that is it for, if I ask you to write short notes on crystal field theory, you will need to give me the definition and the basic assumptions. Okay, I will explain this further in class, but here you have an octahedral complex. So for it to form the complex, there must be d orbital splitting. So the d orbital is going to split into the high energy and low energy. So you're going to have a higher energy level and a lower energy level. At the higher energy level, you have dx square minus y square and dz square. Both of them are called Eg. Okay, and for T2G, you have dxy, dxz, and dyz. So I'll draw a proper diagram in class. So we should have a class for this. Just to summarize everything. Now, advantages of crystal field theory over other bonding theories. So if I'm to ask you for advantages, this is what you're going to give me. It explains colors, explains magnetic properties quantitatively, predicts high spin and low spin complexes, explains stability through crystal field stabilization energy, now predicts geometries of complexes and explains spectrochemical series. So those are advantages of the crystal field theory. Now we are going to, in this section, we are comparing elements in particular groups, and we are going to starting from group 13. So in group 13, we have gallium, indium, and thallium. So I can ask you to compare the three. So maybe give me like three properties, okay, and then you compare the three. So 1, common oxidation states for gallium +3, plus indium +3, thallium is +1 and +3. For metallic character, gallium is moderate, indium is more metallic, and thallium is highly metallic. While for the stability of +1 state, gallium is less stable, indium is moderately stable, and thallium is highly stable. For the oxides of gallium are amphoteric, while the oxides of indium are basic. The oxides of thallium are strongly basic. So take note of that. Now to group 14. For group 14, we are going to be considering germanium, tin, and lead. So germanium, tin, and lead. So for germanium, nature, metalloid, metal for tin, of course, I'm sure you know that, and metal for lead. Oxidation state for germanium is +2 and +4, tin is +2 and +4, lead is just +2. While for the stability of the plus 4 state, germanium is stable. For the plus 4 state is moderately stable for tin and is less stable for lead. Okay, now we can move to group 15. Now for group 15, we are going to be looking at arsenic, antimony, and bismuth. Now, the three properties we are going to be considering, we're going to look at the metallic character. So for metallic character of arsenic, so arsenic is metalloid, antimony is metalloid, bismuth is a metal. While the oxidation states, arsenic you have -3, +3, and +5. Antimony +3 and +5. Okay. While for bismuth you have only +3. Okay, for arsenic, the oxides are acidic. For antimony, the oxides are amphoteric, while for bismuth, its oxides are basic. Now on to group 16, we are going to be looking at selenium, tellurium, and polonium. Selenium, tellurium, and polonium. So these are the three properties. Now we can say for selenium, the metallic character, it is non-metal. Tellurium is a metalloid, while polonium is metallic. Oxidation state for selenium -2 +4 +6, while for tellurium is also -2 +4 +6. But for polonium, of course, the minus cannot exist since it is metallic, so it's just +2 and +4. Conductivity: selenium poor, tellurium is semiconductor, while for polonium you have a metallic element. Okay, on to definition of organometallic chemistry. So we just look at an intro to organometallic chemistry. And for organometallic chemistry, this is a branch of chemistry that studies compounds containing direct metal carbon bonds. Okay, so these are examples. I can ask you to give me a definition with 2 or 3 examples. So these are examples of organometallic compounds. So I'll give you proper structure in class of what an organometallic compound, like that's the ferrocene, look like. Okay, so you are going to get a proper structure. So, but here you have ion sandwiched between two cyclopentadienyl rings. Now for the Grignard reagent, this is quite common. Okay, it's common in chemistry. So you see some symbols R, MgX, where R represents the alkyl group, Mg of course magnesium, and X halide. So this is an example of a Grignard reagent. Now classification of organometallic compounds. So you have ionic organometallics, covalent organometallics, transition metal organometallics, pi complexes. Okay, so those are organometallic compounds. So you should know the examples. You can get more if you wish. So, but these are common examples. These are common examples of each one. Now to roles of metals in biochemical systems. So roles of metals in biochemicals. So metals perform so many functions, and that is why sometimes we take supplements, right? Can take supplements like zinc. Okay, so babies sometimes are given zinc. Even men take zinc. The men can find out why they take zinc. Okay, so and there are several others. Iron. Okay, so these are different metals that are of important. They perform important functions in the body. So one, oxidation transport, 2, electron transfer, 3, enzyme catalysis, 4, photosynthesis, that's for plants, 5, nitrogen fixation, 6, structural stabilization. So those are the rules of metals in biochemical systems. Okay, now we have the HSAB concept. Some textbooks call it Pearson's HSAB concept. That's hard and soft acids and bases. So here we are going to be looking at, so what this is telling us that the concept is simply telling us that a hard base will prefer to combine with a a hard acid, while a soft base will preferably combine with a soft acid. Okay, hard to hard, soft to soft. So now let's look at examples of hard acids. So here you have to take note of two things: the properties of hard acids and examples. Okay, so what are the properties of hard acids? So they have small size, high charge density, and they are poorly polarizable. Examples include H plus, Fe3 plus, and Al3 plus. Now for soft acids, these are the properties. So they have larger size, they are easily polarizable, and examples include silver, okay, that's Ag plus, mercury Ag2 plus, and palladium, that's Pd2 plus. Now for hard bases, so you have um, F minus, OH minus, and NH3 as hard bases. For soft bases, these are examples. So that's I minus, S2 minus, and Pr3. Okay, so what's the principle? Like I said earlier, hard acids prefer to combine with hard bases, while soft acids prefer to combine with soft bases. So that's the HSAB concept. That's the principle. Okay, so you can see examples: soft acid and soft base. So these will people prefer to combine. Now, examples of metals in biochemical systems. So examples of metals in biochemical systems. So take note of this. So iron, for instance, you find it in hemoglobin, and it is important for oxygen transport. Without it, you will not be alive. Magnesium, of course, is at the center of chlorophyll, okay, for photosynthesis. Without it, you not have food to eat, right? Zinc, of course, enzyme activation, okay. So it is a lot of adults zinc supplements. Copper, electron transport, very important. Cobalt, yes, so you find it in vitamin B12, so it's very, very important too. And another one, molybdenum, so that's for nitrogenous enzyme. So these are all metals that are necessary, okay, for proper functioning of biochemical systems. Now to oxidation and reduction. So oxidation means loss of electrons, increase in oxidation number, addition of oxygen, and removal of hydrogen, right? So this is an example of oxidation. Now to reduction is gain of electrons, decrease in oxidation number, removal of oxygen, and addition of hydrogen. So these are definitions for reduction. Okay, so you can see illustrations of redox reactions where you see, for instance, zinc and copper. This is quite common. You can break this overall reaction here. You can break it down into two half reactions. One where you have oxidation, right? Two where you have reduction. So an example would be iron rusting. So for iron to rust, the iron must be oxidized. And see here it is oxidized, right? Oxygen is being added, and that is what you have there. So that's it for the note.